In the final years of the 1980s, at a military airfield in the California desert, a hangar door opened, and something rolled out into the daylight that made the assembled engineers and officers go quiet in a way that had nothing to do with security protocols. It was large. It was dark gray, almost black in certain light. It was flat in a way that no aircraft had ever been flat before. Not aerodynamically flat in the way of a racing aircraft or a supersonic jet, but geometrically flat, as if the concept of three-dimensionality had been applied minimally and reluctantly to a shape that would have preferred to remain a drawing. No tail, no conventional fuselage, no sharp angles anywhere. The entire surface was a continuous curve that flowed from one edge to the other without interruption, like a single piece of material that had been formed rather than assembled. It looked, to the people who saw it for the first time, like someone had cut a section from the night sky and fitted it with landing gear. This was the B-2 Spirit, the aircraft that its designers had built to not exist. Not in the sense that it was a concept or a prototype, but in the sense that its entire purpose was to be present in airspace without any radar system on Earth being able to confirm that presence. An aircraft whose primary capability was absence. A machine whose most important characteristic was a negative, the absence of a radar return, the absence of an infrared signature significant enough to track, the absence of any information reaching an adversary's sensors that would tell them something was coming before it had already arrived and departed. The cost of each aircraft, when calculated to include the development program, the supporting infrastructure, the software, and the specialized maintenance systems without which the aircraft could not operate, approached $2 billion in contemporary value. One aircraft, $2 billion. The entire fleet that was eventually built, 21 aircraft, after the Cold War ended and the procurement justification that had funded the program dissolved, cost more in aggregate than the entire military budget of most countries that maintain armed forces. And the aircraft's operators considered this expenditure justified, because what the money had purchased was not simply a bomber, but an argument. A physical demonstration that a target could be struck anywhere on Earth without the people defending that target receiving any warning that would have allowed them to respond. To understand why anyone spent that much money on that argument, you have to understand what American strategic planners were looking at when they sat in front of their classified assessments of Soviet air defense capability in the mid-1970s. The Soviet air defense network of that period was not a single system, but a layered architecture of overlapping capabilities that had been built, refined, and expanded across 3 decades of Cold War competition. Surface-to-air missile batteries covered approaches at multiple altitude bands. Fighter interceptors could be scrambled to cover gaps. Early warning radars provided detection at ranges that gave the defense time to prepare responses. The whole system was integrated through command networks that could coordinate responses across wide geographic areas. American defense planners had studied this architecture in detail and had reached a conclusion that was uncomfortable but clear. In the event of a conventional conflict requiring strikes on Soviet territory, American aircraft would be detected, tracked, and engaged well before they reached their targets. The losses would be severe. The missions might not succeed. The logic of stealth, reducing an aircraft's radar cross-section to the point where it was effectively undetectable, had been understood theoretically for years before anyone had the computational tools to actually design an aircraft around it. The physics were established. A surface that absorbed radar energy rather than reflecting it, or that scattered reflected energy in directions away from the receiver, would appear smaller on a radar screen than its actual size. Make the surface small enough, and you could make a large aircraft appear on radar as something the size of a bird. The practical challenge was designing an aircraft that achieved this characteristic while still being able to fly, carry weapons, operate its own systems, and be built in a factory from materials that actually existed. Two major defense contractors received funding to investigate whether the theoretical physics could be translated into practical hardware. One of them moved faster, produced a result earlier, and built the tactical strike aircraft that went on to limited but operationally significant service in the late 1980s and early 1990s. A faceted design whose angular surfaces, while odd-looking, reflected radar signals in controlled directions away from the transmitter. The other contractor moved more slowly and aimed higher. Not a tactical strike aircraft, but a strategic bomber capable of reaching any point on Earth from bases in the continental United States, carrying enough weapons to constitute a serious strategic capability, and doing so without being seen. The competition for the strategic stealth bomber contract concluded in October 1981, when the Pentagon announced that the team built around the slower-moving contractor had won. The winning design was based on a concept that had a historical precedent reaching back to the late 1940s. The flying wing, an aircraft configuration in which the fuselage and the wing are effectively the same structure, with no separate tail surfaces and no cylindrical body extending beyond the wing envelope. The flying wing configuration was aerodynamically attractive for efficiency reasons, but had been largely abandoned because it presented control challenges that the hydraulic and mechanical flight control systems of the post-war period could not reliably address. By the early 1980s, digital fly-by-wire control systems had advanced to the point where those challenges were manageable, and the flying wing's aerodynamic advantages, combined with its inherent suitability for low observable design, made it the obvious foundation for what the program required. The engineering team began work on a design that would become one of the most consequential and most expensive aircraft programs in aviation history. Almost immediately, the program encountered its first serious complication. The original requirement had specified a high-altitude aircraft, a bomber that would approach its targets at altitude, relying on its low observable characteristics to avoid detection and engagement. Before the design was finalized, the military customer changed this requirement, adding a low-altitude terrain-following capability that would allow the aircraft to fly beneath radar coverage in areas where that approach was tactically relevant. The addition of this requirement was not a trivial modification. An aircraft designed to fly efficiently at altitude and an aircraft designed to fly safely at low altitude have different structural requirements, different aerodynamic characteristics, and different systems architectures. Adding the low-altitude capability to a design that had been optimized for high-altitude operations required reworking significant portions of the engineering. The program schedule extended by approximately 2 years, and the cost increased by an amount that, in contemporary dollars, would approach $2.5 billion, before a single production aircraft had been built. The facility where the aircraft was built was not purpose-designed for the program. A former automotive manufacturing plant in California, which had been acquired by the contractor and converted for aerospace work, housed the production operation behind walls that gave no external indication of what was being assembled inside. The workforce was substantial. Hundreds of engineers, technicians, and manufacturing personnel working on a program whose existence was publicly acknowledged in general terms, but whose technical details were protected by security measures that went well beyond what most classified programs required. Every person with access to the program underwent background investigations that extended beyond their own personal history to include the histories of family members, close associates, and anyone else whose relationship with the employee might create a potential vulnerability. The intent was to ensure that no one with access to the program's technical details had any connection, however indirect, that could be exploited by a foreign intelligence service. The measures were extensive and, in 2 documented cases, insufficient. The first case came to light in 1984, when federal investigators identified an engineer who had been transferring technical information about the program to Soviet intelligence for a period that the investigation did not precisely establish. The engineer was arrested, prosecuted, and sentenced to a term in federal custody that extended to nearly the end of the following decade. The second case surfaced more than 20 years later, when another employee connected to the program was found to have been providing technical data to Chinese intelligence. This individual received a sentence of several decades in federal prison that remained active at the time of this account. These 2 incidents, separated by 2 decades, illustrated both the value that foreign intelligence services placed on the program's technical details and the difficulty of completely securing a large, complex engineering program that necessarily involved hundreds of people with detailed knowledge of sensitive technology. The security measures in place reduced the risk substantially, but could not reduce it to zero, because the fundamental vulnerability was not the physical facility or the documentation systems, but the human beings who carried technical knowledge in their memories. While counterintelligence operations were dealing with these incidents, the engineering teams were continuing to work on the design challenges that the aircraft's unprecedented requirements generated. The aerodynamic configuration of a flying wing without conventional tail surfaces required a flight control system that could compensate for the aircraft's inherent tendency toward instability in certain flight regimes. The digital control computers that managed this compensation processed sensor inputs and generated control surface commands at rates that no human pilot could match, making corrections continuously to keep the aircraft flying in a stable manner that felt natural to the crew. Without these computers operating continuously, the aircraft was not flyable by human inputs alone. The shaping philosophy that gave the aircraft its distinctive visual character was itself the product of computational advances that had occurred in the decade preceding the program's most intensive development phase. The specific challenge in designing a low-observable aircraft is that the physics of radar reflection are counterintuitive for complex shapes. A flat surface reflects radar energy in a highly directional manner. Most of the reflected signal goes in one direction, and if that direction is away from the radar receiver, the surface appears very small on the radar screen. A curved surface scatters reflected energy in multiple directions simultaneously, which sounds as if it would reduce detectability, but actually complicates the design problem, because the scatter pattern depends on the precise geometry of the curve in ways that require computational analysis to predict and optimize. The computational fluid dynamics tools that became available in the second half of the 1980s allowed engineers to model how radar energy interacted with complex curved surfaces in detail that had previously been impossible to calculate. This made it possible to design the aircraft's outer surface as a continuous curved shape, every panel blending smoothly into every adjacent panel without sharp transitions, that scattered reflected radar energy in controlled directions that minimize the return reaching any receiver. The resulting shape, which resembled nothing in previous aviation design, was not arbitrary. Every curve was where it was because the computational analysis showed that curve was optimal for the radar signature management objective. The materials from which the aircraft was constructed were selected for both structural and electromagnetic properties. Carbon graphite composite materials made up a substantial fraction of the airframe, a choice that provided strength and rigidity at lower weight than metallic alternatives, while also contributing to the aircraft's electromagnetic signature management, since composite materials interact with radar energy differently than metals. The outer surface was covered with a specialized coating, whose precise formulation and application process were among the most closely guarded technical secrets of the program. A multi-layer structure that absorbed and diffused radar energy at the wavelengths that air defense systems used. The radar cross-section of the completed aircraft, the parameter that quantifies how large an object appears on radar, was reduced to approximately 1 square meter, a figure that needs comparison to be understood. A conventional strategic bomber presents a radar return roughly equivalent to a large building. The B-2, by contrast, appeared on radar at the same scale as a large bird. The distinction is not merely quantitative. A radar operator looking at a screen showing a large, bright return responding in a manner consistent with a powered aircraft has no question about what they are looking at. A radar operator looking at a screen showing a return the size of a bird, moving in a straight line at constant speed, might notice that something was unusual, but by the time that observation had been processed, communicated, and acted upon, the aircraft would have completed its mission and departed. The 4 engines that powered the aircraft were embedded within the wing structure in a configuration specifically chosen to minimize their infrared contribution to the aircraft's overall signature. The hot components of a jet engine, the turbine stages and the exhaust nozzle, are the primary sources of infrared emission that heat-seeking sensors can detect and track. Placing the engines inside the aircraft's structure, rather than in external pods or underwing nacelles, allowed the wing's surface area to shield the hot components from direct line-of-sight observation from below and from the sides. The exhaust gases were directed through specially designed nozzles that mixed them with cooler ambient air before they exited the aircraft, reducing the temperature of the exhaust plume to a level that was substantially less detectable than a conventional engine exhaust. The absence of afterburner capability was a deliberate design choice with direct signature implications. Afterburning, injecting additional fuel into the exhaust stream after the main combustion stage, produces a dramatic increase in thrust, but also a dramatic increase in temperature and infrared emission. An aircraft using afterburner at night is visible to the naked eye at substantial ranges. For an aircraft whose entire value rested on not being detected, afterburner capability was a liability rather than an asset, and the designers accepted the speed limitation that came with its absence. The B-2's maximum speed was subsonic, substantially slower than the supersonic performance of dedicated interceptor aircraft, because speed had never been the point. Being present without being detected was the point, and subsonic speed with undetectable signature was more useful for that purpose than supersonic speed with a visible afterburner trail. The crew of 2, a pilot and a mission commander, with provision for an additional crew member in certain configurations, managed the aircraft through an automated systems architecture that handled a substantial fraction of the workload that would otherwise require human attention. The cockpit contained multiple large multifunction displays presenting sensor data, navigation information, weapons system status, and aircraft systems health. The integration of these systems allowed the 2 crew members to manage a strategic bomber of unprecedented capability without the larger crew sizes that earlier generations of strategic aircraft had required. The automation was not merely convenient. It was operationally necessary, given the mission durations that the aircraft was designed to support. A strategic bomber based at a single location in the continental United States, capable of reaching any target on Earth without requiring forward basing, would spend many hours in the air on any meaningful mission. The crew needed to be functional and effective when they arrived at the target area after many hours of transit. Managing the aircraft's systems manually throughout that transit, without automation to handle routine tasks, would have degraded the crew's performance at the moment when it mattered most. The automation handled what it could handle automatically. freeing the crew to rest in shifts during the transit portions of a mission and to focus attention on the target area when they arrived. The provision of toilet facilities and food preparation equipment in the cockpit was a practical response to this reality rather than a luxury. A mission lasting more than a day in each direction required the crew to meet basic physiological needs in the confined space of the cockpit. The equipment that addressed these needs was installed with the same engineering care as the weapons systems and the flight controls, because crew incapacitation from exhaustion or physical discomfort was as real a mission risk as mechanical failure or enemy action. The aircraft's weapons capacity was commensurate with its size and its strategic mission. 2 internal weapons bays together accommodated a payload of up to approximately 18,000 kilograms, a figure that could be filled with nuclear gravity bombs, conventional precision-guided munitions, cluster weapons, anti-armor submunitions, naval mines, or cruise missiles, depending on the mission requirement. The ability to carry nuclear weapons was central to the original program justification, but the flexibility to carry conventional precision weapons proved operationally significant in ways that the Cold War program rationale had not fully anticipated. The aircraft had no defensive armament of any kind, no guns, no air-to-air missiles, no active jamming systems designed to defeat incoming weapons. The design philosophy was explicit and uncompromising. The aircraft's defense was its invisibility, and any system added to address the scenario where that invisibility had failed would add weight and complexity that would compromise the primary capability. If the aircraft was detected and engaged, the design philosophy acknowledged, the outcome was likely to be unfavorable, regardless of what defensive systems were installed. The investment in defense against that scenario was better spent on making the scenario less likely to occur. The first public appearance of the aircraft came at a ceremony in November 1988 at a California production facility. The event was carefully staged. The aircraft was positioned for photographers to capture its frontal profile, and the angles from which photography was permitted were controlled to prevent images of the rear section, where the exhaust nozzle design incorporated features that the Air Force was not prepared to reveal. The journalists who arrived at the ceremony to photograph what the country had been building for nearly a decade encountered a security arrangement that was thorough but had a gap. The airspace above the facility had not been restricted. A group of aviation journalists who recognized this fact hired a light aircraft and flew over the facility during the ceremony, photographing the aircraft from directly above. The images they obtained showed precisely the exhaust nozzle design that the ground-level photography restrictions had been intended to protect. The episode became one of the more celebrated examples of investigative ingenuity in military aviation journalism, and it illustrated a general principle that the military would encounter repeatedly in subsequent years. Restricting access at one level does not prevent access at another level that was not anticipated. The program's cost, through the research and development phase alone, reached figures that required a new vocabulary to describe. The aggregate research and development expenditure through the late 1980s translated to tens of billions of dollars in contemporary value, before accounting for the unit cost of each production aircraft. The production cost per aircraft, including the infrastructure and support systems that each aircraft required, was itself a figure that would have funded the entire military establishment of a modest-sized nation for multiple years. These costs had been justified to congressional appropriators throughout the program's development on the basis of the threat environment that the aircraft was designed to address. The Soviet air defense network was real. The difficulty of penetrating it with conventional aircraft was documented. The value of an aircraft that could bypass it entirely was genuine and large. The argument held as long as the threat environment held. In November 1989, The wall that had divided the German capital since 1961 was breached by crowds who had decided, effectively simultaneously, that they were no longer willing to respect it. The political and military architecture that the wall had represented followed it into irrelevance over the subsequent months, and in December 1991, the state that had been the primary justification for the entire American strategic arsenal dissolved without the conflict that arsenal had been built to deter ever occurring. The B-2 was entering its operational phase in a world where its primary adversary had ceased to exist. The procurement plan that had envisioned over 100 aircraft was revised downward, then revised downward again, and ultimately settled at 21, a number that represented a fraction of the force that would have been required for the aircraft to fulfill the strategic mission for which it had been designed at anything approaching its intended operational tempo. The first operational use of the aircraft came during the NATO air campaign in the Balkans in the spring of 1999. The aircraft flew from their permanent base in Missouri, a distance that required crossing the Atlantic Ocean and significant portions of European airspace, struck targets in the former Yugoslavia, and returned to Missouri without landing at any intermediate location. The round-trip missions lasted approximately 30 hours each. In the total mission count of the air campaign, the stealth bombers represented a small fraction, perhaps 50 sorties out of tens of thousands. But the American military claimed that these missions accounted for roughly a third of all targets struck during the campaign. 6 aircraft flying from the center of the continental United States, flying missions that kept their 2-person crews in the cockpit for more than a day at a stretch, had produced a disproportionate share of the campaign's results. The Afghan campaign that followed the September 2001 attacks produced a mission that extended the already remarkable endurance records established in the Balkans. 1 aircraft flew from the continental United States to targets in Afghanistan and returned without landing, a mission that kept its crew in the cockpit for 44 hours. 2 pilots, confined to the cockpit of their aircraft for nearly 2 consecutive days without the ability to stand up properly, change altitude in a meaningful sense, or sleep in a way that allowed genuine recovery, completed what was, at the time, one of the longest continuous combat missions in aviation history. The aircraft flew in subsequent operations over Iraq and Libya as well, building a combat record that consistently demonstrated the same pattern. Small numbers of sorties, producing results that would have required much larger conventional forces, because the ability to arrive undetected eliminated the layered defensive responses that any conventional strike package would have encountered. The accident that reduced the operational fleet from 21 to 20 occurred in 2008 at a base in the Western Pacific. The aircraft crashed on takeoff. Both crew members ejected successfully and survived. The investigation that followed identified a cause that was simultaneously mundane and humiliating for a program that had spent billions of dollars addressing every conceivable high-technology vulnerability. Moisture had accumulated in air pressure sensors mounted on the aircraft's exterior surface. This moisture caused the sensors to transmit inaccurate data about temperature and airspeed to the aircraft's flight control computers. The computers, operating correctly on the basis of incorrect inputs, generated control surface commands that were appropriate for the flight conditions the sensors reported, rather than the actual flight conditions. And the discrepancy was sufficient to cause the aircraft to depart controlled flight at low altitude, where recovery was not possible. An aircraft worth approximately $1.5 billion had been destroyed by water. The implications of this loss extended beyond the immediate accident. The production line for the aircraft had been closed for years by the time of the accident, and no mechanism existed for building a replacement. Every remaining aircraft became irreplaceable, in a way that influenced how the fleet was operated, what missions it was assigned, and what risks its crews were permitted to accept. 20 aircraft spread across potential operational requirements that a force of over 100 had been designed to address created a management challenge that had no clean solution. The maintenance requirements that the aircraft imposed were themselves a significant operational constraint. The low observable coating that covered the aircraft's surface was not a conventional paint that could be reapplied as a routine maintenance procedure. It was a multi-layer engineered system whose performance depended on the precise application of each layer and on the integrity of the complete structure. Any damage to the coating, from weather exposure, from contact with foreign objects, from the stresses of normal flight operations, could increase the aircraft's radar cross-section by a margin that compromised the core capability the coating existed to provide. After each flight, maintenance crews inspected the aircraft's surface systematically, identifying any areas where the coating had been damaged and performing the repairs necessary to restore it to specification. The ratio of maintenance hours to flight hours that this process produced was, by any comparison to conventional aircraft, extraordinary. For every hour the aircraft spent in the air, it required many hours of maintenance on the ground, and a significant fraction of those maintenance hours were specifically devoted to preserving the invisibility that justified the aircraft's existence and cost. The aircraft were housed in specially designed structures at their home base that maintained controlled temperature and humidity conditions. The materials from which the aircraft's coating was made were sensitive to environmental exposure. Extended periods in sunlight caused degradation. Rain and temperature cycling created conditions that could cause the multi-layer structure to separate, and the general atmospheric environment of an outdoor flight line was damaging in ways that required constant remediation. The hangars that protected the aircraft from this environment were themselves substantial investments that had been built specifically for this purpose and could not be repurposed for conventional aircraft. The combination of these factors produced an operational capability that was real and significant, but constrained by the aircraft's rarity, by the cost and difficulty of maintaining each example, and by the impossibility of replacing any aircraft that was lost. American strategic planners had to manage these 20 aircraft as objects of irreplaceable value, while simultaneously using them in operations where any aircraft theoretically faced some risk, however small. The resolution of this tension between the aircraft's operational utility and its irreplaceability was addressed partly through the development of a successor that had been progressing through the earlier stages of the acquisition process. The successor program, which carried a designation suggesting its intended relationship to the aircraft it would eventually replace, was substantially more closely held than the B-2 program had been at comparable stages of development. The available information was limited to official statements of intent and a single computer-generated image released by the Air Force. The image showed a flying wing configuration that maintained the conceptual lineage of its predecessor while presenting a silhouette that appeared smoother and more fully integrated. The impression of a design that had taken the B-2's approach and refined it further, with 2 additional decades of advances in materials, manufacturing, and computational design tools. The planned retirement date for the B-2 fleet had been revised significantly from original projections. Where early program documents had anticipated operating the aircraft into the 2050s, a service life that would have approached 70 years, a figure achieved by very few military aircraft in history, more recent planning documents reflected an intention to retire the fleet by the early 2030s, contingent on the successor program progressing on schedule. The logic was straightforward. Maintaining 20 aging aircraft whose support infrastructure was unique and whose operating costs were enormous made less sense once a more capable successor was available in meaningful numbers. Until that successor arrived, the 20 aircraft continued to fly. They appeared periodically over major public events in the United States, large sporting occasions, ceremonies, events where a flyover by military aircraft was traditional. The B-2's appearance at these events produced a particular quality of reaction from people who saw it for the first time. The combination of its size, its shape, and the absence of the acoustic signature that normally announces an aircraft's approach created something between wonder and unease. It was large. It was silent, in the way that an aircraft with no exhaust pointing downward can be nearly silent at low speed from below. It looked like nothing that anyone expected to see in the sky, and it moved through the air with a quality that the word glide describes better than any word associated with powered flight. Each such appearance cost money. The operating cost per flight hour for the aircraft was a figure that would have provided a meaningful fraction of an average annual salary, and each flyover consumed multiple flight hours. The Air Force's willingness to incur this cost for public appearances reflected a calculation about the value of reminding potential adversaries, potential allies, and the domestic public that the capability existed and was operational. A weapon that nobody knows about is a deterrent only to the people who know about it.
A weapon that appears in newspaper photographs and social media posts that millions of people have watched fly over a football stadium is a different kind of argument. The B-2 had been designed for a specific world, a world defined by the confrontation between two superpowers, each attempting to develop military capabilities that could defeat or neutralize the other's most formidable systems. It entered service in a different world, used its capabilities in conflicts that its designers had not anticipated, against adversaries that had not existed when the program began, and survived long enough to be planning for replacement by a third-generation program whose capabilities the current operators could only partially describe. What it demonstrated, across 3 decades and multiple operational deployments, was a principle that was both simple to state and extraordinarily difficult and expensive to realize. That the ability to be present without being detected is, in the right strategic circumstances, worth an extraordinary amount of money. The argument was never cheap, and it was never without controversy, and it was never without the operational constraints that come from having a capability concentrated in a very small number of irreplaceable machines. But the aircraft that rolled out of that California hangar in 1988 and made the assembled engineers go quiet had made its case in a way that the people who had built it, and the people who had flown it, and the people who had tried to shoot it down without knowing it was there, all agreed on, even if they could not always agree on everything else. It was real. It worked. And for the decade when its existence had been the most closely guarded secret in American military aviation, it had been the edge of what was technically possible, the outer boundary of what engineering and physics and unlimited budget applied to a single purpose could actually produce.